Hello, everyone. I'm Prerna Shekhar Bharadwaj, and together with my classmates, Rushil, Neil, and Subhadra, we will be presenting to you a technique for training vector representations of words that capture their meaning in an intuitive way that is also useful for natural language processing by computers. Vectors trained in this way are called GLOW vectors, which is an abbreviation for the title of the paper we are presenting, Global Vectors for Word Representation. Next slide, please. Before we begin with the specifics of our paper, let us define what it means to mean something. Historically, there have been three schools of thought. The first believes in distributional semantics. That is, a word is characterized by the company it keeps. In the example sentence on the slide, we could fill in the blank as, we all had to smile for the camera. That is, the context is predictive of the missing word and vice versa. Thus, a representation of a word that is predictive of a typical context in which it occurs is considered a good representation of its meaning. The paper we are presenting deals with distributional semantics because it is generally applicable and does not need human experts to annotate data or design features and representations for semantics. The other two theories of semantics, like frame and model theoretic semantics, are less practical and apply to sentences. Next slide, please. Now we will talk about different types of word representations and the rationale for which one to choose. Next slide. The simplest option to represent a word or any categorical variable for that matter is to construct a one-hot vector for it. Each vector size is equal to the total size of the vocabulary, which can be huge. All entries are 0 except for the single index associated with this word. One obvious reason why such a representation is dispreferred is that the vectors can be huge if the vocabulary is large. Not only is this a problem by itself, but when fed as input to a machine learning model, it also inflates the size of that model, since it will need to have parameters associated with each dimension. A bigger issue, however, is that in this one-hot representation is all words are equally similar or dissimilar to each other. Assuming distance is measured via cosine similarity or Euclidean distance, for example, the word friend is just as similar to the word buddy as it is to enemy. Next slide, please. To alleviate these issues, we force words to share dimensions with each other, and by using dense vectors where most values are non-zero, such vectors are typically called embeddings. Each vector is represented by a vector of size d, which is typically much smaller than the vocabulary size. This alone does not solve all the problems with one-hot vectors though. We still need a way to learn dense embeddings from data such that each dimension has some unique attribute that it corresponds to. For example, whether the word is referring to a living or a non-living being. We have to learn dense embeddings from data such that similar or related words have smaller cosine or Euclidean distance than dissimilar or unrelated words. We need to learn dense embeddings from data such that attributes of a word can be added or removed via simple arithmetic operations like addition and subtraction. For example, if we subtract the embedding of the word man from the embedding for king and add the embedding for women, we should end up with queen. And lastly, embeddings should be easy to visualize. Next slide, please. Everything I said begs the question, how can we learn word embeddings that satisfy these requirements? In the following slides, we will learn about two different strategies to do this. These are both relevant since GLOW embeddings is the subject of the paper we are presenting, which combines both of these strategies to compensate for each other's weaknesses and build on their strengths. Now, my teammate Neil will talk about the first strategy.
Hi. So the first strategy to learn useful word embeddings is to perform dimensionality reduction on a matrix representation of words and the context in which they occur. This dimensionality reduction should yield a matrix where each row corresponds to the representation of a word. The immediate questions are, how do we represent words as well as the context in which they occur is a matrix, and how do we perform dimensionality reduction? In the Word document occurrence matrix, each row corresponds to a word while each column corresponds to a document in dataset. If the ith word in the vocabulary occurs in the ith document in the dataset, then the ijth term in the matrix is set to 1, otherwise it is 0. In the word co-occurrence matrix, both columns and rows correspond to words, thus such a matrix is a square. However, the ijth term is equal to the number of times that the ith and jth words in the vocabulary occur within some maximum distance from each other. Here, distance is measured as the number of words in between them. Word document co-occurrence matrices are typically used for search and retrieval type tasks. For general natural language processing tasks, we use the word-word co-occurrence matrix. The remaining question is, how do we perform dimensionality reduction? The strategy here is to apply a technique called singular value decomposition. It decomposes a matrix W of dimension Mn into the product of three matrices: a square matrix U of dimension Mm, a rectangular diagonal singular value matrix S of dimension Mn, and another square matrix V of size N. Typically, we truncate the matrix S by include only the top k rows. Let this matrix be S. So we then evaluate the dot product of matrices U and S to get a matrix of dimension MD. In our use case of training word embeddings, the rows of this matrix are the word embeddings we seek. Thus, we have only one way to extract word embeddings from data. But is this the only way? But we also need negative samples which tell us what words should not occur in what context. We derive these by randomly replacing either the target word or context words within its window. We can now formulate a binary classification task to predict whether a certain target word and context around it form a positive or a negative sample. So, how to predict? How can we formulate a model to perform this binary classification? We simply use a logistic regression model. This makes use of two different kinds of embeddings. Theta W is the dense word embedding we would like to learn. Beta C is an embedding for all the context words put together. This needs to be derived somehow from embeddings of the individual context words. Assuming we have each of these, the probability of a word occurring in a given context is defined by the formula on the slide. We can define a binary entropy loss function and train this model using stochastic gradient descent. One remaining detail is the method of deriving the fronttext representation from embeddings of words. There are two approaches here. We can simply add up all the embeddings of context words. This is called the contextual bag of words approach. Or we perform a separate prediction for each that is target word and context word pair. This is called the skip-gram approach. So now we will compare the above methods. Each of the methods that we have talked about so far can derive usable word embeddings. However, they each have different strengths and weaknesses. Dimensionality reduction is much more efficient than prediction in contextual windows and makes use of large corpora better, since we don't have a sample to subset of contextual windows. However, prediction in contextual windows has been shown to produce interpretable word embeddings, which cluster related words together and have dimensions that capture unique semantics. The key question then is how can we combine both of these? This is what the authors of the paper have succeeded in doing. So now my teammate Rushil will describe this in detail.
Hello. So before we move on to the global vectors approach, let us define some terms. So the first is x of I, which is denoted as the number of times the ith word, which we will denote by v of I, occurs in the database. X of ij is the number of times the word v of I and the word v of j co-occur in the database within a small window. One thing to note is that x is a symmetric matrix of the co-occurrence frequencies. P of ij, which happens to be the probability of word v of j occurring, that word v of I is given, will be x of ij divided by x of I. W of I is taken to be the target word embedding vector column for the word v of I. And wk is taken to be the context word embedding column for the word v of k. Next slide. So let us start by defining the optimal condition that the word vectors should satisfy. The left-hand side of the equation is the dot product between the target word embedding and the context embedding for each word within a contextual window of it. This is similar to logistic regression model we defined earlier. The right-hand side, however, is the log of the probability of target and the context words co-occurring. One issue here is that the denominator of P of ik only depends on the target word W of I rather than the context word. Thus, it is incorrect to expect the dot product of their embeddings to capture the denominator term. To deal with this, we introduce a bias term B of I associated with the target word, as you can see in the equation. We also include a bias term B of k to retain the symmetry between the target and the context embeddings. This gives us the second equation on the side. However, this is merely a definition of optimality. The question comes, how do we actually achieve this? Next slide. So one approach is that we treat this as a linear regression problem. Target word and context embedding are initialized randomly. We evaluate the weighted mean square error between the left-hand side and the right-hand side of the equation on the previous slide for each target and context sample in the data set. We use gradient descent to change the target word and the context embeddings in such a way that this error is minimized. But the question comes, why do we use weighted mean square? So the answer is that we do so to prevent very frequent co-occurring word pairs from overwhelming rare co-occurrences, which might actually be more useful for learning word embeddings. So for example, the word the co-occurs in numerous times with almost every word, especially if the contextual window is wide. By limiting the maximum weightage of such common co-occurrences to 1 and increasing the weightage of rare co-occurrences, we mitigate this issue. This is what function f of x does. Next slide. Okay. So to summarize, GloVe efficiency uses statistics on the whole corpus x of I and x of ij to train word embeddings rather than randomly selected contextual windows. GloVe uses regression model to train word embeddings, as we saw before. It also uses dot products between word and context embedding, which ensures each vector dimension carries isolated and unique semantics, and that does not mix with other dimensions. Also, it can produce interpretable embeddings that are easy to visualize and are compatible with the vector arithmetic to modify the semantics. Now my teammate Subhadra will go over some results and visualizations for this.
Hi, I'll be discussing about the semantic clustering. In this process, we first cluster words based on similarity between their word embeddings as mentioned by Euclidean distance. As we can see, the clusters seem intuitive. The first cluster includes words with same sentiment, such as adore, love, admire, embrace, rejoice, and etc. The second cluster captures all the animals, such as leopard, dhole, warthog, rhinoceros, lion, and all the other animals. The third cluster also captures synonyms, antonyms, such as bad, decent, excellent, lousy, nice, and all the emotions. Next slide, please. Apart from clustering words together based on meaning, We can also perform vector arithmetic to add and remove semantics. Consider the two-dimensional embedding of the word king. Let us subtract the embedding for man. As you can see in the graph, now let's add the embedding for woman. We can see that the net position of this embedding is the closest to the two-dimensional embedding for the word queen. Here are some more examples of such vector arithmetic. For example, consider the embedding of the word Paris. Let us subtract the embedding for France. Now let's add the embedding for Italy. We can see that the net position of this embedding is closest to the embedding for the word Rome. Another example is consider the embedding of the word Windows. Let us subtract the embedding for Microsoft. Now let's add the embedding for Google. We can see that the net position of this embedding is closest to the embedding of the word Android. Apart from such cool visualizations and word analogies, these word vectors can be proved as features to machine learning models for tasks like named entity recognition. As we can see from table, the maximum F1 score is obtained by using glove vectors as features on multiple benchmark datasets. Hopefully, you all enjoyed that talk and learned something interesting from it. We would like to sincerely thank Professor Richardson for giving us this opportunity. Thank you.